Good morning, everyone. Welcome back to day two, DVCon India 2021. I hope you enjoyed day one content. Just to remind you, we are in track three. In this track, we will be covering primarily workshops. So today we have two workshops to cover. We'll be starting with a workshop from Rambus. As you all know, data is a new oil, and data is driving the whole industry. Data which is generated by gaming, medical, a lot of other applications are demanding next generation data centers and cloud solutions. And memory playing very important role in the data center and cloud, as we all know. And Rambus is leading designer for memories for decades. And today we have Sanjay, who will be talking about high speed and bandwidth DDR5 memory buffer clocking more than 5,600 MTS per second for enabling next generation data centers and cloud solutions. Sanjay Munchini has 20 plus years of semiconductor industry experience, and he is currently leading the buffer chip business unit at Rambus India Division Center. His previous work experience is with Qualcomm, Intel, Texas Instruments, and Synopsys. He has extensive knowledge and experience working hands-on and leading teams on complex SOC designs, IP level verification activities in simulation, emulation, and formal, including flows and methodologies. He has also worked on post-silicon validation, custom sampling activities. Sanjay was the keynote speaker at Mentor Verification Forum 2017. He has 9 IDFs filed and 1 patent approved. He has a master's in computer engineering and MBA in entrepreneurship from USA. He had a privilege to chair DVCon Accelerator Day conference for past 3 years. Welcome, Sanjay. Let's have the video.
Hello everyone, thank you for joining the Rambus workshop. I'm Sanjay Muchini from the Rambus India team, and I'm responsible for the buffer chip business unit that delivers high-speed memory interface chips to the semicon industry. My team in India works on various aspects, starting with design and verification and all the way to tape out and silicon bring-up activities. And today we are going to discuss the topic high performance DDR5 Gen 2 5600 megatransfer per second buffer products that will enable the next generation data centers and cloud solutions. We have a packed agenda with topics covering introduction of Rambus and its products. Then we will look at the server performance demands, the key differences between DDR4 and 5, and then we will jump into the design and verification activities specific to our Gen 2 buffer chip. So let's begin to the next slide. Rambus is an industry pioneer with over 30 years of advanced semiconductor design experience that develops and licenses chip interface technologies and architectures that are used in digital electronic products. The company is well known for inventing RDRAM, which is the Rambus DRAM that subsequently led to the synchronous DRAMs in the early 90s. Rambus produces products and innovations that address the fundamental challenges of accelerating data. Rambus has 3 major product lines: the memory interface chips, the high-speed interface and security, silicon IP. Let's talk a little more details onto each of these different product line, starting with memory interface chips. Made for high speed, reliability, and power efficiency, our DDR memory interface chips for registered, load reduced, and non-volatile dual inline memory modules, which are in short called the RDIMMs, the LRDIMMs, and the NVDIMMs respectively. And these products deliver top of the line performance and capacity to the next wave of enterprise and cloud servers. Rambus offers DDR5, DDR4, the DDR3 interface chips on both the RCD and DV. We'll talk a little bit more into what this RCD and DV stand for. But just let's go with the flow right now, and we'll talk more on the different DIMM chipsets which have these RCDs and the data buffers. So as I said, the memory interface chips cater to the needs of the data center server chipsets that demand high performance computing and high memory capacity. These buffer chips, as I said, come in two different configurations. One is the DBs. You can see the acronym DB. DB stands for data buffers for buffering your data signals, and the RCD, which is your registered clock driver, for buffering clock and command address signals driven by CPU host. 3 generations of buffer chips for DDR3, 4, and 5, along with RCD support for non-volatile memories are supported by the Rambus product line. We'll discuss more on the details of these memory buffer chips in the upcoming slides. As you all are aware, memory is one of the largest spend categories in the server today, and it continues to grow with the increasing demand for higher bandwidth and capacity as compute performance in the data center continues to increase. The near-term transition to DDR5 will double the max data rate and bandwidth, and it will also quadruple the DIMM capacity with higher DRAM densities and improve the power and memory access efficiencies. In the midterm, the addition of coherent serial links in the server architecture like CXL, which is your Compute Express link, has the opportunity to enable further capacity expansion, flexibility between DRAM and storage class memory, and the introduction of new memory tiers to address the bandwidth and latency gap between the CPU attached memory and storage. A long-term view, we will see the rack level architecture continue to gain traction that leverage a disaggregated architecture, separating compute, memory, and storage into pooled resources for better utilization and improved latency as well. With each technology and architecture progression, the speed and performance of the interface between the processor and the memory is critical for the overall performance of the system, and that is exactly where Rambus sits right in the center. CXL is the new memory interconnect standard, which is going to focus on the expansion and, as I mentioned, on the memory pooling concept with the advanced data center architectures. So one of the key important features of pooling is devices can be logically partitioned up to, say, 16 hosts. And in this example, you can see, you can also very flexibly match the memory resources to what is needed for a particular workload. For example, the host, say H1, uses all of D1 and half of D2 and a quarter of D3. That is one particular workload and how the CPU can distribute the workload on the different memory devices. The host 2 can use all the devices, and all the hosts can simultaneously access D1, each getting a dedicated partition of the allocated memory bandwidth. So CXL will take us into a different level of memory expansion in the future. High-speed memory and high-speed interfaces are critical for data-intensive applications. And Rambus Silicon IP portfolio, which includes the memory PHY and digital controller for DDR3 and 4, the GDDR6, the HBM, in the lower process nodes, provide the required solutions in that particular space. SerDes PHY and digital controller for the PCI Gen 5 and CXL 2.0 are also part of the course offering. These are silicon proven solutions and are critical to high performance data centers, networking, AI, machine learning, and automotive applications because they enable and optimize the transfer of data between chips and electronic devices. With the growing threat environment, hardware-based embedded security solutions are mission critical for protecting various applications. The Rambus security IP solutions include crypto cores, the hardware root of trust, the high-speed protocol engines, and chip-level provisioning technologies. Now that we have looked at all the different key product lines of Rambus, we will now move into the memory interface chips. Memory interface chips are buffered modules introduce basically a memory buffer between the memory controller and the DRAM devices on each of the module, isolating the DRAM from the memory bus and enabling an increase to the width of the memory without increasing the pin count of the controller. This reduces the effective capacitive load on the memory bus, enabling support for multiple modules at high speed. Buffered modules also provide the added benefit of being able to compensate for signal attenuation and latency between the memory controller and modules without introducing any additional pins to the controller. Those are some of the key advantages of having buffered modules. The modules that are more physically distant from the controller than the others will have higher access latencies than those that are closer to the controller at high speeds. Because of this variation in access latency, back-to-back memory references that access different modules may incur a so-called a bubble on the memory bus, which will result in a loss of efficiency. To increase efficiency, the buffers can be designed to insert varying amounts of delay to equalize the access latencies of all the modules in the memory. By doing so, back-to-back memory references can be pipelined to increase memory system effective bandwidth. So I think those are some of the key features of why we need interface chips and how they enable the overall throughput and the system performance. So this is a visual diagram of how the CPUs connect to the dual inline memory modules. The DIMM stands for dual inline memory modules. And you can see the memories are populated on the DIMM chipsets. And the DDR5 RCD is, again, we have DDR4 and DDR5 RCD. Here we are talking about the DDR5 RCD and two configurations of the RCD. One is your registered DIMM, where you have just the RCD, and you have load reduced DIMMs, where you have the data buffers, which is the DB, and the RCD as well. So these are two configurations of the DIMMs, which are extensively used in the server configuration. And as I said, the primary function of the buffer chip or the RCD is to buffer the command and address bus, the chip selects, and the clock between the host controller and the DRAMs. So that is the primary function of the RCD. It also, again, as I said, creates a BCOM bus interface which communicates with the data buffers. and controls. And there is a control and a handshake between the RCD and the DB. There's a communication link here. As I mentioned, enterprise and data center servers need high memory bandwidth and capacity to feed multiple cores inside the processor, utilize the DIMM modules. The JEDEC committee has works on the standards for the definition of both the RDIMMs and the LRDIMMs to improve the capacity without degrading any signal integrity and continue to maintain high speeds. So in summary, RDIMMs and LRDIMMs utilize buffers to reduce loading and improve signal integrity at high speeds to improve the overall capacity and bandwidth of the servers. I hope the concept of the DIMMs and the buffer DIMMs is clear from this slide. Let's move on. And let's talk about the server performance and some of the evolving server needs for the next generation. As you all know, servers are driven by the fact that they have become the center of cloud computing and AI. And there are a expanding number of workloads, which means that the servers are looking for higher performance, looking for more capacity, and to also adapt to various different workloads that have to serve the needs of the applications. And we'll see that the general performance workloads will be moving from nearly 500 gigabytes per system, which is a benchmark from the last year's data, to nearly 800 gigabytes per system in 2025. So that is the average usage of the data compute that each of the server is going to process. And these are if you have to summarize the key driving factors or the needs of the demands of the server, this slide pretty much captures all the key bullets. Again, like we discussed, we need increased capacity per system, and DDR5 must provide those large capacity in gigabytes. That increased capacity must be delivered to the processor at a higher bandwidth. So it's just not the capacity, we need higher speed and access to the memory. That is the second point. And as we all know, the processor wants to receive data in units of cache lines. So the access granularity of the memory request on the memory channel must remain 64 bytes. So this is not going to change. The reliability of the interface, DIMMs and DRAMs must be the same or better as today. Moving on to the other important factor is the power. The key challenge to scaling server performance is the ability to remove heat from the chassis and control the temperature. Today, the DIMMs are typically designed to stay within a 15 watt per DIMM envelope, and that has remained relatively unchanged. So this is going to continue, that even though we push the higher capacity and a bandwidth, we will have to maintain the power within this particular budget. Finally, the time to bring up, the system boots up, we want to make sure that the bring up and the memory training must be controlled and should not impact the expected boot time. So these are some of the key features or the demands from the server side as we go into the next generation, and which DDR5 is going to address all of these. So here we are going to look at what are the key changes between, say, the DDR4 and the DDR5. I have used LRDIMM as a reference, which has both the data buffers and the RCDs. The concept of RDIMM and LRDIMM are unchanged from DDR4, although there are significant changes in the configuration of the module itself. Let's discuss the data channel. The data channel in a DDR4 module is a single memory interface channel and delivers 8 bytes of 64 bits of data, again, one cache line, each clock phase along with 8 additional ECC protection, which brings you to a total of 72 bits. The burst length of DDR4 is 8 clock phases per read and write transaction. So a single transaction will deliver 64 bytes of data, which is a cache line. The burst length in DDR5 has been increased to 16 clock phases to increase channel efficiency. So you will see double the burst length in the DDR5. To maintain the access granularity of 64 bytes, the DDR5 module is split into two independent channels, sub-channels, which is channel A and channel B. You can see on the picture here illustrated. And each channel is 40 bits wide, 32 bits for the data plus 8 bits of ECC. Again, in order to maintain the same ECC protection while also allowing for storing of metadata. So you will see a DDR5 DIMM has two more additional DRAMs, or in a 2-rank DIMM, you have 4 additional DRAMs. The additional channel per module not only satisfies the access granularity requirement, but it increases the parallelism of the memory operations and data sets because of the dual channel concept. Second, let's look at the, we have discussed the data part. Now let's look at the command address and clock bus, which is the control plane of the DIMM. The DDR4 uses 33 bits pins running at single data rate with respect to the clock. In order to fit two independent command address buses on the DDR5, this interface had to get much more efficient. So in DDR5, we retain a single clock for both these channels. The commanded address has been reduced to 10 pins. So there are 10 pins per channel, each running at dual the rate, at dual data rate, like the data plane. So the data plane is already at a double data rate. Now in the DDR5, we are going to look at double data rate for the command address as well. Finally, let's compare the raw speed of the data channel. While DDR4 tops at 1600 into 2, which is your 3200 megatransfers per second on a dual data rate, DDR5 will launch at 4800 megatransfers per second, which is the first generation. And now we are talking about 5600, which is your generation 2. And it has been designed to reach all the way to 8400 megatransfers per second, which is quite a big leap from the existing DDR4 speed, what it can achieve. So moving ahead, I think this is a good table which summarizes the key differences of the DDR5 RAM and module architecture as compared to the DDR4 and its advantages. So you have the DDR4, the DDR5, and some of the advantages here. We covered the speed. We talked about the speed, the channel architecture in the previous slide, the burst length, and of course the CA bus changes, which we're going to do a double data rate on the CA pins versus the single data rate in the DDR4. These changes increase your overall bandwidth, increase efficiency, and lower loaded latency in the same module connector footprint as a DDR4. So DDR5 must deliver more capacity per module. This is done by increasing the maximum density per die from 16 GB to a 64 GB in DDR5. So for a DIMM using single die package, SDP stands for single die package, DRAMs, The maximum capacity will increase from 64 gigabytes to 256 gigabytes. And higher capacity DIMMs can be realized again through 3D stacking technology. DDR4 uses 8 high stack using 3-bit chip ID field, whereas DDR5 will support 16 high stack using a 4-bit chip ID field for all densities except the 64 gigabit. So higher performance and capacity can come with higher power, as that is the trade-off. But DDR5 well lowers the operating voltage. So yeah, I think if you see the I/O voltage is going to reduce from 1.2 to 1.1, and the command address signaling is going to change to a pseudo open drain logic signaling, which has the advantage of burning no power when the pins are parked in high state. So this also gives us additional benefit of low power in the DDR5 architecture. So moving ahead, folks, we just talked about the RCD. There are a bunch of other companion chips which are going to make way onto the DIMM chipset. And you can see there are other chips which are being developed for the DDR5 DIMMs. Some of them are the the power management PMIC chip, the hub, and the temperature sensor. The hub communicates. The hub or serial peripheral detect chip communicates interrupt requests and services from the slave devices like temperature sensor, PMIC, and request the host to address the request coming from these slave devices. And temperature sensor will help in making adjustment to the system thermal limits. Due to the high speed, there is a potential of thermal runaway as well. So in summary, DDR5 includes more intelligence on the DIMM. With these 5 components that we just discussed, to scale the server performance as the number of CPU cores increase, require more capable DIMMs than just a simple increase in the capacity. This is accomplished with the offloading of intelligence from the CPU to the server component that can be done more efficiently on the chipset itself, on the DIMM chipset. So now we have seen the various needs of the server markets and the high-speed memory interfaces. What are the needs of the next generation? What are the key differences between your DDR4 and 5? Now let us look, let's take a little deeper view into the design and verification aspects of the RCD. This is the high-level RCD design block diagram, and it shows all the key building blocks of the chip. And as you can see, there are 3 major interfaces for the RCD. One is your host interface, which is your CPU interface. And as we discussed, there are 2 channels, channel A and channel B. And you have the DRAM interface, which is the memory side interface. And there's also a data buffer interface. Like we talked, there are data buffer communication between the RCD and the DBs. So this interface takes care of that. And we also have the sideband interface. The host can access this I3C, I2C interconnect. It's a low-speed interconnect, which the CPU can access to configure any registers or read any status registers. So this is the high-level picture of how the RCD looks. And if you look a little more closely, this is a mixed signal chip with a digital top, and you can see high-speed transmitters along with the clock and the command address going to 2 channels. And you also have the receiver side, the signals received from the host side, where you have your receiver circuits, which will have channel equalization circuits like your DFE and CTLE. Plus, you have your high-speed clocking. We do not route the same clock coming from the host. We have to generate a high-performance clock internally and distribute the clock to the different channels on the transmitter side, ensuring that the data path is, again, low latency, and it has to maintain the speed, 5600 megatransfers per second. So we have to take care of the speed, and also to ensure that the signal quality is not compromised. The system, if you really see in a nutshell, is more geared towards how do we do system trainings on the different pins on your DRAM side. You look at your calibration sequences. Your protocol has to be maintained. You have to make sure you're not violating any DDR5 protocol during any and all operations coming from the host side to the memory. So all of these circuits need a lot of precision in understanding the circuit design and also implementing the circuits in full custom layout to achieve this kind of high-speed data transfer. And of course, the other challenges or the opportunities are with the verification team, which has to verify the digital portion of the chip and also the interaction between the digital and the analog blocks in the design. And we're going to look at some of those opportunities and also the challenges in the verification in the next couple of slides. So moving to the verification, this is the top level test bench, which we use to verify our design. I've taken RCD as your design under test. And you can see that we have the UVM components. You have your host driver, and we have two host drivers to drive traffic. This mimics the CPU host and drives both the channels into the, we have two channels, as I mentioned, so you'll need two instances of the host UVC to drive traffic into the RCD. And then you have your sideband UVC component, which drives the sideband traffic. You also have your DVCon, which is your data buffer interface, which is more like a passive component and will capture the commands coming out of the RCD on the DVCon interface. And on the QCA side, which is your Q side, which is your memory side, you have another passive component which will capture all the commands coming from the RCD towards the DRAM side. So we have covered all the interfaces, the host side, the sideband, this is the in-band, this is the sideband, this is the data buffer interface, and this is your memory interface. We have scoreboards and monitors in the environment, along with assertions at different assertion checkers are present to make sure, I think we check for any glitches, delays, incorrect values getting propagated into the stimulus. And the goal at the end is to, I think, ensure that the functional and code coverage is enabled, and we verify the complete design as per the JEDEC spec. Is the overarching goal for the verification team. So moving ahead, this is the other snapshot of the LRD, where you have the design also having the data buffer instantiated in your test bench. And like we discussed, there are UVC components like the host, which would drive the RCD and also the DB. So you have the host side and the DRAM model, which is going to receive and respond to the requests coming from the host side through the RCD and through the DB. So moving ahead, I wanted to quickly touch base on a couple of important verification components of the RCD. One is your register verification. Post the initialization sequence, we perform the trainings on both the host and the DRAM side. I'm going to talk a little bit on the trainings for the input pins and the output pins. What are the critical pins and how do we do training? And once we do the training, we proceed with the functionality verification along with the register program. This is just a quick snapshot of the global control register that can be programmed to control the device into different data rates, which is a single data rate or a double data rate. And you also have power down, there's a bypass mode, transparent mode, etc. We want to make sure we cover registers, not just for register coverage, but also what each register is being programmed and how that translates into functional verification as well. So there are two aspects of the register verification. Moving ahead, like I discussed, we have training sequences for both the host side, the signals coming in from the CPU side, and also the outputs of the RCD and the DV have to be trained through, I think one is the programming sequence in these control registers for both the RCD and the DB interface. We'll discuss more on the trainings in the next slide. I'm going to only talk about the RCD host and the DRAM. In the interest of time, I'm not going to touch on the data buffer trainings aspect. So moving on to the host side training, there are two critical trainings. One is your chip select training. The D stands for the host side. That's the convention we use. And DCS training mode is the primary goal is to align the DCS with respect to the DCK. This is the input clock coming from the host side. And when we program random delays on the DCS and the DCA, which is your input command address, and check that the DCS is being sampled as expected by the RCD. And once the sampling is accurate, we send out the response, which we capture on the alert and signal, and send it back to the host. So in this training mode, through the sideband, since the host command path is not calibrated yet, we use the sideband to program the training sequence, the training command. And we also want to make sure that the DCK is running and the DCA and the D power signals are ignored in the beginning because we are still not in the functional mode. The RCD will sample the DCS signal on every rising edge of your DCK. And every set of 4 DCS signals on 4 DCK rising edge samples are captured by the RCD. And there is a logical computation which it does internally to determine the output result. And then it calculates that and sends out the output with a logical 0 or 1 based on what is the sequence and what is the expected output. And this result will be sent back to the host. And that completes the CS training or the DCS training. Now, if you move on to the DCA training, which is your host side command address training, again, we program the random delays on the DCS and DCA and check whether the samples are as expected by the RCD. And the response, again, is captured on the alerts and signal. In this DCA training mode, the DCK will be running and the DCS, which is your chip select, will qualify when to sample the DCK and the CA and the CA signals. In this, what we do is there's a loopback equation which results in an output value based on what we sample on the CA. So we do a logical computation, which is mostly an XOR based computation to see the bits which are coming on the DCA. And then RCD decides whether that logical computation, the XOR values are accurate with the expected result. and then it sends out the response back on the alert end to the host. And there are very particular timing requirements of between each of the event, how long can it take for each of the event to get triggered, and when to have the valid and the exit as well. So we have to make sure all the timings are also maintained. Okay. Moving on, I'm not going to spend a whole lot of time on the DFE training mode. Again, this enables the use of pattern comparison. DFE stands for decision feedback equalization. This is an equalization technique to make sure your receiver receives is calibrated or trained to make sure all the input signals are well received without any loss of signal attenuation, etc. So there are a whole lot of details to it, but the two important modes are the manual mode and the training and the accelerated training modes. The accelerated training mode gives you more sweep control on the capacitance values on the circuits to fine tune the receiver gain. So at the end, I think all equalizations circuits will target improving the gain of your received signals, right? So that's the primary objective of this circuitry, and we have to tune this circuit as well. Moving ahead, there are two important pins, output pins on the DRAM, which is your Q side. Again, we indicate the memory side with the Q and the host side as a D. So the QCA training calibrates the DRAM command address bus with respect to the incoming DCK. Here we verify that the host side DCA is passed. So the DCA gets passed to the QCA. Again, if you observe, this is a 7-bit DCA, whereas you will see that the CA is a 14-bit. It's a double data rate. So that's where you will see the packing of the command address, and it moves to the memory side. So we use unidirectional delays to model the QCA delays with respect to the QCK. Again, the training is more to align the QCA sampling with respect to your DCA. So that is the high-level summary. Again, there are details of how different ranks and can be enabled and trained for each of the corresponding chip selects. I think I'm not going to go into those details for now. And moving on, I think the QCS, which is the chip select on your memory side, again has to be trained, and we do in a similar way. Again, we have a particular registers which we write to in the RCD that generates a continuous clock pattern on the QCS. If you see the QCS QA, which is the channel A and channel B, you can see that the clock starts toggling on this QCS pin, and there's a particular calculation based on the encoding of these patterns, and that is captured. And again, I think you will see the training exited after you get a particular response. Okay. So the low power modes, RCD supports multiple power down features like power down enable and the self-refresh entry mode. So again, DDR5 does not have any separate clock enable signals going to the DIMM or the DRAMs. So most of it is controlled through the signaling by the QCS or the DCS. So the chip select becomes an equivalent of a CKE, and it drives either an active or an inactive state for the DRAM side. That is the high-level description of this low power mode. Again, I think moving on to the self-refresh. Self-refresh mode is a very low power state in which the input clock, if you see, there are two modes, with and without the clock stop. This is with the clock stop. You can see that the clocks stop here on your QCK, and the system enters into a self-refresh mode in both the modes, and it also exits. If you see, there are two commands, the SRE entry command, which comes from the host, And once it is in the entry situation condition, it goes into a self-refresh mode, and it exits when the host sends 3 back-to-back knobs. If you see, the knobs will trigger an SRX command, which is your exit command as well. So it comes out of the self-refresh mode once it sees a back-to-back 3 knobs. So moving on, folks, I think we have discussed the training aspects, the register programming of both training sequences of both the host side and the memory side. We also, the verification challenges are also centered around how do we verify the mixed signal aspects, like I discussed. We have a mixed signal design, and we have to make sure that the models which we use in our RTL simulations, the behavioral models correlate with your SPICE simulations. So this is a big challenge. And then we have to make sure that the chip connectivity aspects, all the way from the sub blocks to the top level, all the connectivity is maintained, including the analog to the digital boundary. And we have to make sure there are no interface bugs between the two domains. Plus, of course, we have to ensure our DFT functions at speed and across various PVT corners. Meeting all aspects of coverage is extremely critical. Like we all know as verification engineers, the functional, the code coverage, which includes the block, statement, expression, toggle, apart from the FSM as well. We have to make sure all these are covered, including the assertion coverage that gives us high confidence that the silicon is, once the silicon arrives, it is bug-free. So folks, I think this is the last slide I have. You can see that the clocking waveform, this is, by the way, the recent press release from Rambus. You can find it on our website. Rambus has sampled the first Gen 2 DDR5 RCDs, and it is first in the industry, and you can see it gives tremendous advantages in terms of latency, and also making sure we are within the power envelope, and we are ready for the next generation servers to use the buffer chips along with the memory, of course. So what I wanted to highlight is, if you can see the clocking waveform, and the data I is really healthy. It looks tall and wide, which is very important for sampling any high-speed signal. So this is a snapshot of our 5600 silicon results. This is not simulation results, these are silicon results. And what I wanted to emphasize was the result of all the exciting work from the design team and exhaustive verification done by the team, pre-silicon and post-silicon, has resulted in a high-quality tape-out and a fully functional silicon, which is clocking at 5600, again, data transfers at 5600 megatransfers per second. So it's pretty exciting, folks, I think, and just wanted to end the presentation with this last slide showing the silicon performance as well. Thank you, and we can open up for any Q&A right now.
So while we wait for audience questions, so I have a couple of questions for you, Sanjay, to start. All right. I think memory verification is one of the biggest challenge when you look at the SOC level or subsystem level, right? So any suggestions or any guidance that you want to share with audience in terms of if somebody is starting from scratch about their memory controller or memory subsystem verification, any top three things that they need to be worried and focused?
It's a great question. So folks, the controller, the PHY, I think it is pretty complex in terms of the functionality. So basic thing I would say, I think we start off with the basic functionality, right? We have to make sure the controller has been verified for the basic operations, the basic commands, and move forward from there to ensure, I think, all the advanced features are also covered with randomization. We also have to make sure we do not leave any gaps from end-to-end kind of verification. We just don't do just the controller plus a model. I mean, you have to really hook up the system level scenario, and at the end, you would want to also use the software drivers in a way to put it into your UVM methodology to have the same sequences and settings to ensure you're not out of sync with what eventually will be done on the software. So I would approach in a stepwise fashion, folks. This topic is a very big topic, but I would say we have to divide and conquer and go in steps and ensure that you have 100% functional coverage. Again, as I said, make sure the model is accurate, whatever models you use in your test bench. And again, at the end, as I said, it has to correlate with how the use cases, how the software is going to use and calibrate your controller and file. So I would say that's how I would approach the problem.
Nice, Sanjay. I think audience, if you have questions, please type in the chat window, and we'll be reading out to Sanjay. Right. Feel free to ask your questions and doubts, and Sanjay is expert, can help you out with the answers. So while we wait for questions, Sanjay, one more question. So typically, memory verification involves both the digital and analog components, right? So again, do you want to throw some light in terms of what kind of guidance that you can give to the audience in dealing with analog portion of the verification?
This is a very interesting and important topic, Lokesh. Like as you mentioned, the interface between the digital and the analog creates a lot of different challenges. We have to have better mixed signal verification. Again, when you use, say, it depends on the complexity of your design. Right? If you have a large design with too many circuits, having the SPICE, what do you call, instantiation of the SPICE netlist will slow down your entire simulation. So one is your simulation throughput is going to suffer. So what we typically do is we have equivalent behavioral models, which we plug it into your top level simulations, and then make sure your behavioral models give you the end-to-end RTL verification with the digital only kind of thing. But then the fundamental problem will arise when your the SPICE versus your behavioral models will get out of sync, and on the silicon you will see that there is a mismatch, or you will find bugs, right? So I would say you have to really do bottoms up, where you really look at all your behavioral models you use and the SPICE correlation. And again, you have to pick your critical path blocks, and one is use top level simulations to do your critical path simulations or critical features. At the sub block or module level, you would have to do behavioral model versus SPICE, as many as you can within your time allocated project time.
Okay, Sanjay, I think it's good. I think one final question from the audience. I think they're primarily asking about, when you deliver your IP to your customer, what are the components, the verification components you do deliver along with IP, like a test bench or assertions or coverage, anything that you package it out?
So right now, I mean, on the IP side, what Rambus delivers, again, I can talk from a buffer chip product side. So buffer chip is a product group. So my group, we deliver the actual silicon. We partner with the fabs, and we manufacture. We are fabless anyway, so we partner with on some of the fabs, and we ship out the actual silicon product to the memory vendors. Like we have the top 3 memory vendors like SK Hynix, Samsung, and Micron. That is from a buffer chip product portfolio. From an IP standpoint, what I understand, again, I think we have the the soft IP and the hard IP. So again, in the soft IP, when we do the just the RTL transfer, I'm sure we bundle most of our environment, the test suites, and of course, with all the documentation which it goes, plus the entire methodology of how we do our internal verification as well. So this is my understanding of the IP course team. But again, as I said, I am more from the buffer chip team, which is a product team, and we focus on really shipping out our silicon.
Okay.
Thanks.
Thanks, Sanjay. I think with that, we'll end your session. Thanks for joining us and sharing your thoughts and ideas on the memory from the Rambus side of it. Thank you very much again.
Thank you, Lokesh. Thank you all for listening in. Bye.
Bye, Sanjay.